the notes for Unit 4, day 8, and because they start on page 23 of your packet. So the focus for this note session is approximating values of a function using local linearity. So if you picture a function that is, it's got some sort of curvature, but if we zoom really far in, it almost looks like a line. And so since we know how to write tangent line equations, we're going to try to approximate values close to where we're zooming into, using that tangent line to approximate the function value. So the essential question then is, how do I use that tangent line to approximate values of functions? So this isn't in your notes. This is just a little bit of background information, but please actively listen and engage your mind as we're looking at this conceptually. So the idea here is that we've got this curve, right? This happens to be the square root of x. And I also have a tangent line drawn at x equals 4. And if I zoom in, and I'm still zooming in, but looking at the scales, you can see I'm zooming in, zooming in. You know, right now I'm just I'm just looking at, you know, basically the immediate surrounding of x equals 4. You can see that the curve and the tangent line basically look like they're the same. But there's a very insignificant amount of difference as I go away from x equals 4 by a tenth of a value, you know, about by tenths, like 4.1, 4.2, 4.3, you know, as I go away from this x equals 4 to 4.1, you know, right here, the function and the tangent line look like they're one and the same. So the idea is, instead of trying to find the square root of 4.1, I could just use the equation of the tangent line and get an approximation that's pretty close to the actual value. So that's what local linearity is called. And so let's try to estimate 4.36, right? So I've already zoomed in a fair amount compared to my original picture. And 4.36 is about right here, maybe? Okay, so this is how we use a tangent line to approximate something that might not be so easy to take the square root of. So I want to know the value of the square root of 4.36. And that's super close to the value of x equals 4. And so instead of using the radical function, instead of using this radical over here, that function, the square root of x, we know that, you know, the square root of 4.36 is slightly bigger than 2. But if I back up to x equals 4 and get the equation of that tangent line, then we can see that at 4.36, the tangent line and the curve are really super close together. So that's blue, so that's using the line. If I'm traveling on the line, I see that that the line and the curve are super close together. And if I zoom in, right, I'm really zooming in now. Now I can start to see a gap, but I really have to zoom in. I mean, the grid on the video right now is only what, 5 thousandths. That's the scale on the grid. If you look between the two gray lines, if you look at the scale at the bottom, 2 squares is 1/100th. So half of that is 5 1,000ths. And so if I get this equation of this tangent line, the blue is the tangent line, I'm gonna have a slight overestimate, right? Because the blue line is on top of that tangent line is above the curve because of the curvature of the square root of x. But that's going to be a decent approximation instead of having to use the square root function. So so for any function f of x, we can write the equation for the tangent line. right? We've been doing that all year. So what are the two things we need? Well, we need a point and we need a slope. Of course, I say slope, you think derivative. And so we're still kind of working with the background information, right? This is all stuff you know. So there's my tangent line, right? This is the point x equals 4, let's say. And of course, when I find the derivative and evaluate it, that's my slope. So we're going to use our equation for our tangent line, and that's going to become the basis for our approximation. So the idea then is, if I write the equation for the tangent line about that point, then I can realistically approximate values close to this location without too much error. I mean, these are, since I'm along the tangent line here, this becomes an approximate value of the value of the function that should be down here, and likewise here. And because of this curvature, and this curvature is called concave down, and because of that curvature, that tangent line is an overestimate. And so that actual value, as you can see from the graphic, the actual value on the curve is smaller, hence the overestimate. Okay, so what are the nuts and bolts here? Well, I need my point of interest, my point of tangency, and I need to, and that's 4,2. That's my point of tangency. I need to find the derivative of the function, and then I need to evaluate so I can get that slope value, right? So it's 2 and 3 are where the calculus is, right? And then we write our equation in point slope form. So we write our equation of our tangent line. And so these are all skills that you have been doing all year long. And then we can use this to approximate. So down here in the on the graph of the function and the tangent line, you see that the actual function value is right here, and then the tangent line approximation is along the blue line, which is a slightly larger value. And so the tangent line is tangent to the square root of x. And so we're going to think of that as x to the half, right? We're going to find the point of tangency. So the point of tangency is x equals 4. So when x equals 4, y equals 2. And then we're going to differentiate our function and find the slope. So that's 4,2 point of tangency. And so it's step 1, finding that point of tangency, finding the derivative. So we're going to, the point of tangency goes here in our equation of our tangent line. Our derivative is doing the power rule here, so it's going to be 1/2 x to the minus 1/2. And I'm going to rewrite that back in its radical form. And now I need to evaluate it. So the evaluation at x equals 4, square root of 4, is 2, so we have 1/4 for the slope. And we can see that on the graph. This tangent line is pretty accurate, right? We go up 1/4. Well, I guess we really can't go up 1/4 because of our scale. We're not really counting by ones. And so this is just a continuation. So we're just doing a continuation right there, step 3, and then step 4, we're writing the equation of this tangent line, right? So we have y equals mx minus x1 plus y1. So we have 1/4 x minus x1, which is 4, plus y1, which is 2. So that's that point of tangency for 2. Okay, and I have a step 5 here because we're going to extend that. That was our basic, writing the equation of a tangent line. We've done that many, many times this year. So the extension is this. We're going to use this to find the y value when x is 4.36, right? That's really all we're doing in step 5. So what we're going to change the notation a little bit. Whether or not you actually want to change the notation when you work this problem is up to you. But you would be familiar with the notation of the approximation notation because they changed the notation and they used both of just the regular tangent line and the new notation interchangeably. So instead of y, we call it L of x, and the L stands for linearization. So when we call it L of x, we know that we're going to be using it to approximate. And then instead of m, we call this the derivative evaluated at a. And then we have x minus a, because that's my x1, right? That's when we evaluate the derivative. And then plus the function value at a, which is y1. Okay, so this is the notation you'll see for linearization problems. I don't really use it all that much. I really rely on this when it comes to actually calculating the approximate value. And that's totally okay. College Board doesn't care which one you use, but you do need to be familiar with this because College Board uses this and your textbook will use it as well. So let's just use it for step 5. So my L of x is 1/4 x minus 4 plus 2, right? It's exactly the same as the tangent. And now I'm going to go ahead and put in 4.36 for x. And then calculate it. So 4.36 minus 4 is 0.36. 36 divided by 4 is 0.09. So the approximate value is 2.09. So that's our approximation for the square root of 4.36. So that's 2.09. If you actually grab just your calculator and take the square root of 4.36, you get 2.088. So a pretty decent estimate using a process that we've been doing since we've been studying limits. Where it takes the need for your square root key right off the calculator. You don't even really need to get involved. You can approximate this way. And in fact, back in the olden days, when all we had were calculators that added, subtracted, multiplied, and divided, this is exactly how we would approximate square roots. So let's try this with some multiple choice problems. Now, first thing we recognize is that we can use a calculator here. So we are going to be calculating our derivative using a math at 8 key. So we have let function f be the function given by x squared minus 2x plus 3. The tangent to the graph of x of f at x equals 2 is used to approximate the value of the function. Which of the following is the greatest value of x for which the error resulting from this tangent line is less than 0.5? Okay, so kind of a twist here on what they're asking for. What they're basically saying is, I want to have an error of less than 0.5. Okay, so we know that the point of tangency is at x equals 2. So if we graph this as a parabola, right? If we graph this and we set up our window, so we're going to go ahead and do that. So we've got x squared minus 2x plus 3. So we've got x squared minus 2x plus 3. And we've got a window of negative 0.25. We've got 2 decimal points in there. Hold on, there we go. And then we've got 3, 1, negative 1, and 6, it looks like. So we're looking at the parabola there. We're just looking at a very small portion of it. And so that's what it looks like right on our screen. And then I'm going to draw the tangent line. So this is a calculator, right? I'm going to just use that tangent function. And so I'm going to come back here and under the draw function, the draw function is right here. It's in blue, the program key. So second draw tangent. And I want that tangent at x equals 2. So I'm just going to type in 2 and hit enter. And there's that tangent line. And the cool thing is, check that out, right? It gives me the equation of the tangent line. It's 2x minus 1. So there's that tangent line. because we use a calculator, we don't have to do really anything by hand as far as calculating derivatives and the equation of the tangent line in slope point form. Calculator just gives it to us in slope intercept form. And so, whoops. And so we know that, oops, I think I continue it here. There we go. So we know that I'm going to graph that tangent line. So I'm going to come back here. I'm going to go into y2, and I'm going to graph that 2x minus 1. Okay, so it looks like that. And now what I can do is I can start looking at, I'm going to do the table setup to start at 2, and I'm going to count by tenths because I see that we have tenths in the answers here. So I'm going to do my table set, start at 2 and count by 0.1. Only because that's what I see in the answer forms here. So when I do that, I get this table, right? If I could show you the table on the actual calculator. So you can see it looks identical to the one I pasted into the PowerPoint. And so that being the case, we are looking at values bigger than 2, so I don't care about values before 2. And we are looking at a difference of 0.5 in the y values. I want this error to be less than 0.5. So that is, if we look at the table here, right, this difference here is 0.49, and then here, this difference here is this way. This difference is 0.4, 0.64, right? So this is, we can't take 2.8, can't take this value, because that's greater than 0.5. The 2.7 is the 0.49, so it's just less than 0.5. So this would be the maximum distance we could be away from 2 and still be within a half of a point, or a half of a 0.5 within the actual value. In other words, 0.5 away vertically from the real value of the function. So that answer then is 2.7. 2.6 and 5 and 4 are much smaller. The values are much closer together, but not the greatest value. Okay, let's look at example 3. So we want an approximation of the function at 1.5. So this is a little more of a traditional question. We still can use a calculator, and we have this function, and that's why we are able to use a calculator. And we want the tangent line to the graph of the function at pi over 2. So that they're telling us to use that tangent. So we know that we are at pi over 2, and since we can use a calculator, we don't have to calculate that. Let's just clear all this out now. And I'm going to go to my table set, and I'm going to start at, let's see here. I'll start at 0. I'm going to start at 0, and I'm going to count by pi over 2's, right, so that I can get exactly the right thing in my table. And then I'm going to go ahead and put this function in to y1, so 2 cosine x plus 1. So 2 cosine, where's my cosine? There it is, x plus 1. Whoops, look at that, I didn't close the brackets, right? It's pretty important to close those brackets. There we go. And if I graph this, we have this, and 1.5 would be about right here, right? But more importantly, I can go to the table here and at pi over 2, which is my point of tangency, right? Pi over 2. At pi over 2, my value is 1. So I know that at pi over 2, my value is at 1. So I don't have to know my cosine of pi over 2. It's 0, 2 times 0 plus 1 is 1. But I can use my calculator if I need to. Okay, so now I'm going to do my math 8. And so I'm going to put in my dx and my 2 cosine x plus 1, evaluated at pi over 2. And the derivative is negative 1.99999, right? So if we quit out of here and we do our math 8, right, and we put in our variable there, and then we put in our 2 cosine x close the bracket, plus 1, so I'm differentiating 2 cosine x plus 1, and then I want to go over here to pi over 2, and then hit enter. I get this. Now we have to be smarter than our calculator. We know that this means we have a slope of -2, right? This is the approximation on our calculator. It does a numeric approximation, kind of like approximating the value using a tangent line. The calculator, that's actually the algorithm the calculator goes through to find the derivative. So we're going to look at that and think -2. So our equation of our tangent line then is -2 x minus pi over 2 plus 1. So there's our tangent line. And we want to use that tangent line to approximate. We could go back to the calculator to approximate if we wanted to and stick in 1.5. I just simplified this expression, multiplied through by the -2x, and then we can put in 1.5. But this is all calculator driven, so really we could put in 1.5 right here and get the answer right away. It just would be in decimal form. So the reason why I simplified it is because I see a couple of forms here that aren't decimal form. So I'm going through the math here. Right? This is -3 plus 1 is -2, so pi minus 2 is the right answer. But if I would come over here and just put in -2 times the quantity 1.5 minus pi divided by 2 plus what? 1.5 minus pi divided by 2 plus 1. If I would just put in the tangent line with my approximation value there, I would get that. And so that's perfectly fine to do. I wouldn't do this math in the PowerPoint here. I wouldn't do this math in my head. I would use my calculator since I can. And then I would backtrack. I would look at these pi minus 2 and 4 minus pi and see which one gets you the right decimal. So then I would come back to the calculator and I would go, okay, pi minus 2. Yep, that's the same decimal. That must be the answer. So that's how I would handle this with a calculator instead of doing all of this math and all this manipulation. Okay, let's take a look at example 4. I feel like these are not consecutive numbers in my examples for some reason. But hopefully they match the notes. Anyway, so okay, we've got this function. This is for function f. The derivative is 2x plus 1. So we already found the derivative for us. And here's my point. F of 1 equals 4. So we're at 1 comma 4 and approximate f of 1.2. So the really nice thing is it tells you we want the tangent line at 1. So we need to use this point and we just need to evaluate this because this is already the derivative. So we know we have the 0.14. We know we have the derivative, and I'm just going to put 1 in there. So we have a slope of 3. And so we know we have a tangent line of 3 times the quantity x minus 1 plus 4. This is all, of course, no calculator because, you know, the information is just that basic. And notice now I'm going to approximate, but I'm going to keep it as y equals. I'm not going to use that linear notation because you don't have to. And I put the 1.2 there. So we know this 1.2 minus 1 is 0.2. 0.2 times 3 is 0.6. So this answer must be 4.6. So that answer is D. And that's usually how quick most approximations go, right? We've gotten really good at finding the equation of the tangent line. We're just taking it one step further by putting in a value so that we can evaluate a number. Okay, let's take a look at example 5. The function is twice differentiable. That just means we can find the derivative. And it gives us all this information here. So we've got the function as value is 1 or 2, so 2 comma 1. We know the derivative is 4. I say derivative, you think slope. And we know that the looks like the second derivative is 3. Okay, so as well as the approximation of f of 1.9 using the tangent to the graph at t. So that's just reassuring us that all of these values can be used because they're all evaluated at 2. Okay, so we know that we got 0.2 comma 1. That's the fewest piece of information. We've got the derivative, which is 4. That's what this says right here, right? And if I say derivative, we think slope, so the slope is also 4. And so our tangent line looks like that, right? 4x minus 2 plus 1. And so we are going to use that to approximate a value of 1.9. And so 1.9 minus 0.2 is negative 0.1. Times 4 is negative 0.4. So 1 minus 0.4 is 0.6. So that should be the answer there. Whoops, just a quick comment. We didn't do anything with this piece of information. So that's kind of interesting. They just gave you something that, maybe if we used the 3 in the wrong spot, we probably would have gotten this other answer. So that was kind of a teaser piece of information right there. Okay, we'll get back to the classroom. We'll go over the takeaways and discuss any questions on the notes, and then let you look at your topic questions.